Pleasure to introduce today's speaker Sumit Kumar Rano from Indian Institute of Science Education and Research, Bhopal. So he shall be talking on a theorem of Strichartz for multipliers on homogeneous trees. And with this, I would like to invite him to deliver his talk. And I also request all the participants to mute their microphones. Okay, over to you, Sumit.
Thank you, Munada, for the introduction and for giving me this invitation for the talk. So, as Munada mentioned, so I shall talk on the topic a theorem of Strichartz for multipliers on homogeneous trees, and the talk is based on a joint work with Professor Rudra P. Sarkar. So let's begin. So before we go into the details, let's have a quick look at the overview of the talk. So the talk is mainly divided into 5 sections, wherein in the first section, that is a theorem of Rho and Strichartz on Rn, we shall basically state the theorem of Rho, which deals with the characterization of the sine and the cosine functions on the real line, and we shall see its n-dimensional, uh, let's say, extension, which was given by Strichartz, which basically deals with the characterization of bounded eigenfunctions of the Euclidean Laplacian. And then we shall move on to define homogeneous trees and all introduce all notations and preliminaries that we shall use later. After which we will explore all possible variants of the Strichartz theorem on homogeneous trees, and by replacing the standard Euclidean Laplacian by the combinatorial Laplacian on homogeneous trees. And building on this result for the Laplacian, we shall then try to generalize it, the Strichartz theorem, on a broader setup of multipliers on homogeneous trees. And after presenting the results on such a broader setup, we shall restrict ourselves to some notable consequences, such as the heat operator and the spherical averages of functions on trees. So let us begin. So in 1980, J. Rho actually proved that if Fk is a doubly infinite sequence of functions which are bounded with respect with L infinity norm and satisfies the recurrence relation, that d by dx of Fk is Fk plus 1. Observe that Rho's theorem actually characterizes the eigenfunctions of the one-dimensional Laplacian, that is d2 by dx2, with eigenvalue minus 1. And using this observation, actually, Strichartz generalized it to n dimensions by replacing this operator d by dx with the standard Euclidean Laplacian, which we shall denote by delta of Rn. So Strichartz theorem states the following. So he considered a doubly infinite sequence Fk on Rn, which is uniformly bounded and satisfies the recurrence relation delta of Rn, that is the standard Euclidean Laplacian acting on the sequence on a function Fk is equals to Fk plus 1. And from here, he inferred that F naught is an eigenfunction of the standard Euclidean Laplacian with the eigenvalue minus 1. A very important thing to note here is that if we replace this recurrence relation, that is delta Rn of Fk is equals to Fk plus 1, by delta Rn of Fk is equals to some a times Fk plus 1 for some non-zero complex constant a, then we actually get F naught as an eigenfunctions of delta Rn with eigenvalue minus of modulus of a. So we shall come back to that in a few minutes.
For some, A belongs
After
to
that,
C star or
C star means
okay.
non-zero complex
Okay, okay,
constant.
okay, okay. So, okay. Thank you, thank you. Yeah, I understand.
Hmm. Because otherwise it don't makes any sense, right? Means if you take
Okay.
a to be 0, then the recurrence relation actually falls,
Yeah.
isn't it? So that is why. So in the same paper, Strichartz also proved that an exact analog of the Euclidean result holds for the sublaplacian on the Heisenberg group. And this result was later generalized to connected, simply connected two-step nilpotent Lie groups by Bakshi Kumar and Singh very recently. But what is striking to see is that the result doesn't hold for hyperbolic three space anymore. That is, Strichartz demonstrated by using counter example that an exact analog of the Euclidean result does not hold for the Laplace-Beltrami operator for the hyperbolic three space. Later, Kumar Ray and Sarkar actually proved that this counter example can be extended to the Laplace-Beltrami operator on a broader setup of rank 1 symmetric spaces. However, they provide modified versions of the Strichartz theorem for the same. But our interest is to explore whether an exact analog of the Strichartz theorem apply for the combinatorial Laplacian on a homogeneous tree X. So before we go to address this question, let us first see what do we mean by homogeneous tree and what is the combinatorial Laplacian here. So a homogeneous tree, which we shall denote by x of degree q plus 1, here q is a natural number, is a connected graph with no loops in which every vertex is adjacent to q plus 1 on other vertices. Observe that when q is equals to 1, we get a homogeneous tree of degree 2, which is nothing but an additive group of all integers whose geometric and analytic properties differ from higher degree homogeneous trees. So henceforth, we shall always assume our homogeneous tree of degree q plus 1 where q is greater or equals to 2. That is, our degree is always greater or equals to 3. We now fix an arbitrary reference point O in X, and then we define the boundary, which we shall denote by capital of omega, as the set of all infinite geodesic rays, that is, chains of consecutive adjacent vertices that starts from O. Pictorially, a homogeneous tree of degree 3 and 4 can be represented in the following manner. So a 3-degree homogeneous tree is an infinite graph where we can see that each vertex is adjacent to 3 other vertices. And fixing a reference point O, we see that a boundary point is nothing but an infinite geodesic ray starting from O and which is denoted as omega in the dotted lines on the boundary. Similarly, a 4-degree homogeneous tree is an infinite graph where each vertex is adjacent to 4 other vertices. And again, fixing a reference point O, we see that a point omega on the boundary is nothing but chains of consecutive vertices that starts from O, and these are given by the dotted lines as the boundary. So we identify X, that is the set of all infinite, with the set of all infinite vertices, and it is actually a metric measure space, which is endowed with the counting measure, which we shall denote by hash, and the standard graph distance d. By the standard graph distance d, we mean that the distance between any two vertex points x and y is basically the number of paths joining the vertices x and y, number of edges in the path joining x and y. For a vertex point x and some non-negative integer n, we write bxn and xxn to respectively denote the ball and the sphere centered at radius x, centered at x and of radius n. An important thing to note here is that with the counting measure of the ball and the sphere grows exponentially with respect to the radius, and therefore the homogeneous tree is a space of exponential volume growth. We are now ready to define the Laplacian. So given a complex valued function u on x, we define the Laplacian as follows. So LU of x is nothing but u of x, and the second quantity is nothing but the average of the functional values of u at the nearest points at which the Laplacian is evaluated. So now that we have the Laplacian and we know what a homogeneous tree means, let us now ask the question that whether an exact analog of the Strichartz theorem holds for the combinatorial Laplacian on homogeneous tree. In other words, let us take a doubly infinite sequence of functions which are uniformly bounded on the homogeneous trees and which satisfies the Laplace recurrence relation with respect to the Laplacian, that is L of fk is fk plus 1. Then can we infer that f naught is an eigenfunction of the combinatorial Laplacian with respect with eigenvalue minus 1? Well, it turns out that to answer this question, we need to analyze the L infinity point spectrum of the combinatorial Laplacian, which in turn depends on the size estimates of its radial eigenfunctions of the combinatorial Laplacian, which are popularly known as the elementary spherical functions. So let us first see what we mean by the elementary spherical functions. So for z in C, the elementary spherical function phi z is mathematically defined in this way. So we are basically integrating the complex powers of the Poisson kernel on the probability measure space, that is the boundary omega. And from this formula, it actually follows that phi, the function x goes to phi z x is actually symmetric and it is periodic, which means that phi z of x is equals to phi of minus z of x, and that is also equals to phi z plus tau, where tau is nothing but a constant which is given by 2 pi by log q, a constant which depends upon the degree of the homogeneous tree. Not only that, the elementary spherical functions phi z are radial, meaning that phi z of x is equals to phi z of y whenever the vertex point x and y lie on the same sphere, radius sphere. And the most important thing is that the Laplace means phi z's are actually the eigenfunctions. That is, L of phi z of x is equals to gamma z of phi zx. And what is gamma z? Gamma z is actually the entire function which is given by this formula. And in fact, these are the only radial eigenfunctions of the Laplacian, in the sense that given any radial eigenfunction of the Laplacian, it is actually a constant multiple of phi z. Next, we see the L infinity size estimate of the spherical functions, which says that phi z belongs to L infinity of x if and only if our z lies in this horizontal strip, which is the z of all means the set of all complex numbers, such that whose modulus of imaginary part is less than or equals to half. In fact, on this strip, the phi z's are actually uniformly bounded with respect to the variable parameter z. So from this line, actually, it follows that the L infinity point spectrum of the combinatorial Laplacian is actually the image of this horizontal strip, that is all those z in C such that mod of imaginary part of z less than equals to half under the map gamma. That is, the L infinity point spectrum of L is gamma z such that z in C and modulus of imaginary part of z is less or equals to half. And this is nothing but an elliptic region in the complex plane around the point 1, which cuts the real axis at the point 0 and 2. So unlike the L infinity point spectrum of our standard Euclidean Laplacian, which is one dimensional, that is minus infinity to 0, which we denote here by green lines in this picture, we actually lost the one dimensionality when we deal with the L infinity point spectrum of L. But what happens if we don't have the one dimensionality? So let us consider a circle of radius 1 around origin in the complex plane. So if we draw such a circle, we see that it actually cuts the L infinity point spectrum of the standard Euclidean Laplacian at the point only -1. And we actually get a characterization of f naught as an eigenfunction with eigenvalue -1 in the Strichartz theorem, right? However, here we see that since the one dimensionality is lost and it is a ellipse around the point 1, so we actually intersect, this circle actually intersects the L infinity point spectrum of L at infinitely many points. And this is what results in the failure. So let us now see what the counter example is. So let us choose 2 points, Z1 and Z2, from that horizontal strip on which phi Z is actually uniformly bounded, such that gamma of Z1 is not equals to gamma Z2, and the modulus of gamma Z1 and Z2 is equals to 1. That is, we choose gamma Z1 and gamma Z2 between in this R. That is the point of intersection between this circle and the L infinity point spectrum. Accordingly, let us define the W infinite sequence Fk as gamma Z1 to the power k phi Z1 plus gamma Z2 to the power k phi Z2. Then observe that the L infinity norm of Fk, this modulus of gamma Z1 and gamma Z2 will actually vanish because we have taken it from the unit circle, and it only boils down to the L infinity norm of phi Z1 and phi Z2, which both are uniformly bounded in this horizontal strip and uniformly bounded by 1. So combining them, this Fk's L infinity norm is less or equals to 2 for all k. Secondly, if we take the Laplacian on Fk, we see that the Laplacian takes over with phi z1 and phi z2. And since these are eigenfunctions, as we have seen, it will again give us gamma z1 and gamma z2 times phi z1 times phi z2, right? And this together with gamma z1 to the power k will give gamma z1 to the power k plus 1 phi z1 and gamma z2 to the power k plus 1 phi z2. And that is nothing but, by the definition, is Fk plus 1 of x. Therefore, our Fk satisfies both the properties of the Strichartz theorem. However, f naught fails to be an eigenfunction, although f naught here is nothing but a linear combination of two eigenfunctions, but in itself it is not an eigenfunction. Therefore, a precise analog of Strichartz theorem with the L infinity norm doesn't hold. Now let us see what happens if we replace the L infinity norm by weak LP norm. That is, if we replace the L infinity norm of the sequence Fk by weak LP norm, which are some naturally occurring size estimates that are satisfied by the elementary spherical functions. So as we did for the L infinity case, we will first see what is the LP infinity point spectrum, and to see the LP infinity point spectrum of the Laplacian, we need to again analyze the behavior of the spherical functions. So before we do that, let us define some more notations. So let P be between strictly greater than 1 and less or equals to 2. Then we write P prime to denote the conjugate exponent P by P minus 1. Our del of P prime is denoted by the formula 1 by P prime minus half. And our P strip, that is the Henderson-Johnson P strip, SP, which we denote by SP, is nothing but the set of all Z complex numbers such that modulus of imaginary part of Z is less or equals to mod of del P prime. We further assume that our P prime is infinity when P is equals to 1, so that our del infinity becomes minus half and S1 becomes the horizontal strip that we have just seen. That is the set of all Z in C such that modulus of imaginary part of Z is less or equals to half. Regarding, so okay, one thing to note here is that when P is equals to 2, this horizontal strip actually boils down to the real line, that is S2 is equals to R. Regarding the weak LP size estimates of phi Z, we have the following. So when P is greater or equals to 1 and strictly less than 2, we know that phi Z belongs to LP prime of infinity of X if and only if Z belongs to SP. And when P is equals to 2, the behavior is actually different. So phi Z belongs to L to infinity of X if and only if Z is not in S2, but S2, that is R minus some countable set of points, that is tau by 2 Z. Observe that when P is equals to 1, we actually recover the results and discussions, whatever we have done for the L infinity case, because when P is equals to 1, P prime is infinity, phi Z belongs to L infinity, that is L infinity of X, if and only if Z belongs to S1. So from these two facts, we actually we can infer that the weak LP point spectrum of the the combinatorial Laplacian is nothing but concentric ellipses in P depending ellipses in the complex plane around the point 1, 0, which cuts the real axis at gamma of I del P prime and gamma tau by 2 plus I del P prime. So basically, when P is equals to 1, this gamma of I del P prime becomes 0 and gamma of tau by 2 plus I del P prime becomes 2, and we get the biggest ellipse. And as P approaches 2, we actually get a line around the point 1, 0. So here also we see that the one dimensionality of the weak LP spectrum of L is lost, unlike the L infinity spectrum of the Euclidean Laplacian. And therefore, if we draw a circle of radius 1, we see that it actually cuts at only -1 when we consider the Euclidean L infinity spectrum. However, here it cuts infinitely many points if we consider the LP prime infinity point spectrum of L. And therefore, once again, an exact analog fails with the uniform LP prime infinity norm estimate of the sequence Fk. So what shall we do? Let us go back to what we have seen or revisit the Euclidean case once more, actually. So we see that Strichartz theorem actually characterizes all bounded eigenfunctions for which there are non-zero eigenvalues. Because if we take a doubly infinite sequence of functions on Rn which satisfies this recurrence relation instead of this recurrence relation, then that is del Rn of Fk is Afk plus 1 for some complex, non-zero complex constant A, then we actually get a characterization of F naught with eigenvalue minus of mod A. And this is also clear from the picture. Let us see how. Actually, instead of taking the radius to be -1, if we take it to be as mod A for any non-zero complex constant A, then we see that it actually cuts the L infinity point spectrum of the Euclidean Laplacian only at one point, that is minus of mod A. And therefore, we get a characterization of F naught as an eigenfunction with respect to the eigenvalue minus of mod A, right? However, for every such choice of A complex constant, this is not the case for the LP prime infinity point spectrum of L, because one dimensionality is lost. And we have seen in particular, if we choose mod of A to be 1, we do not have the proper analog. However, if we take our radius to be as gamma of tau by 2 plus I del P prime, and then draw a circle of radius this, then we see that it actually cuts the LP prime infinity point spectrum of L only at one point. Similarly, if we take our radius to be as gamma of I del P prime, it actually cuts the LP prime infinity point spectrum of L again only at one point. Therefore, we actually have to change the recurrence relation, that is L of Fk is equals to Fk plus 1, to be L of Fk is equals to AFk plus 1, such that modulus of A is equals to gamma of I del P prime or gamma of tau by 2 plus ideal p prime to get a characterization of eigenfunctions with respect to these two eigenvalues. This is what actually the picture tells us. And we will shortly see that this is actually the case. And secondly, when e is equals to 2, as I said, that the L to infinity point spectrum actually degenerates into a line segment around the point 1, and it is actually an open interval, and therefore the one dimensionality is preserved as in the Euclidean case, and we actually see that this is mainly the Euclidean type of thing, means for the p is equals to 2 case. So let us now see the theorem for Strichartz theorem for the Laplacian. So this is the p is equals to 1 case where we consider a doubly infinite sequence of function fk on x, which are uniformly bounded, and replace the recurrence relation L of fk is equals to fk plus 1 by L of fk is equals to a fk plus 1, where a in C satisfies modulus of a is equals to tau by 2 plus ideal infinity. What is tau by 2 plus ideal infinity? This is the point. Then our f naught is an eigenfunction of the combinatorial Laplacian with eigenvalue gamma of tau by 2 plus ideal infinity. For p strictly between 1 and 2, that is greater than 1 and less than 2, we suppose that f is a bi-infinite sequence of functions on x, such that the weak LP norm, LP prime norm of fk is less or equals to m for all k in z, and then we have the following results. That is, we take one-sided sequence in both the cases to characterize these two eigenvalues. That is, L of fk is equals to a fk plus 1 for all k in the positive part of the sequence, where a in C satisfies modulus of a is equals to gamma of ideal p prime. Then L of f naught is gamma of ideal p prime of f naught. And if we take the negative side of the sequence satisfying this recurrence relation, that is L of f of minus k is equals to a f of minus k plus 1 for all k in n, where a is a complex constant satisfying mod of a is equals to gamma of tau by 2 plus ideal p prime, then L of f naught is equals to gamma of tau by 2 plus ideal p prime of f naught. Observe that the p is equals to 1 case and p strictly greater than 1 and less than 2 case are different, at least in couple of grounds, despite the fact that the L infinity point spectrum of L and the LP prime infinity point spectrum of L, both of them have lost the one dimensionality and are elliptic regions. And what are the differences? Firstly, we see that here we do not get any characterization of f naught corresponding to the eigenvalue gamma of I del infinity as we had got here, that is gamma of I del p prime. That is because gamma of I del infinity is nothing but 0. And Strichartz theorem cannot characterize harmonic functions. This is the drawback. Secondly, for gamma of tau by 2 plus I del infinity, here we consider the doubly infinite sequence satisfying this recurrence relation. However, here we take only one-sided, that is the negative part of the sequence, right? This is because 0 belongs to the L infinity point spectrum, and which doesn't belong to the LP prime infinity point spectrum, as we can see from this picture. So for LP prime infinity, it is away from 0. However, if we see the L infinity point spectrum of the combinatorial Laplacian, we see that it actually touches 0. That is why we had to take the double infinite sequence to characterize this eigenvalue 2. However, only one-sided sequence is enough to characterize the eigenvalue gamma of tau by 2 plus ideal p prime, since 0 doesn't belong in the LP prime infinity point spectrum of L. And the second case, that is the p is equals to 2 case, which we have proved, is the following. That is, if fk is a bi-infinite sequence of functions on x which satisfies that the L to infinity norm of fk is less or equals to L, and L of fk is a fk plus 1 for all k in z, where a in C satisfies mod of a between the open interval 1 minus b comma 1 plus b. This open interval is nothing but the L to infinity point spectrum of the combinatorial Laplacian. Then L of f naught is equals to mod of a times f naught. So here we can see a big difference between the p case, that is p strictly less than 2 case, and p is equals to 2 case, in the sense that Strichartz theorem actually holds for all points in the L to infinity spectrum. However, when we deal with p strictly less than 2 case, we only get a characterization of these 2 points, that is gamma of I del p prime and gamma of tau by 2 plus I del p prime. This is the major difference between the p case and the 2 case. In fact, the 2 case actually exhibits a lot of a Euclidean behavior, and therefore we shall not be interested anymore in the 2 case, and we shall be interested more towards the L, means the p case analog, when And if we replace this Laplacian, let's say by spherical averages, ball averages, or let's say the polynomial of a Laplacian, what happens if we replace this L by these functions, or more generally multipliers, and not only any multipliers, multipliers on Schwartz spaces. So before we deal with or formulate the theorem of Strichartz for a broader setup of multipliers on Schwartz spaces, let us first mathematically define what we mean by multipliers. And since we need to define multipliers on Schwartz spaces, we need to know what are the Schwartz spaces here on homogeneous trees. So let's begin. So the spherical Fourier transform f hat of a finitely supported function f on x is defined by this formula, that is f hat of z is nothing but the summation against the phi zx. And since phi z is symmetric and periodic, so does fz. So that is f tilde of z is equals to, f hat of z is equals to f hat of minus z, and that is equals to f hat of z plus star. Secondly, the Helgerson Fourier transform f tilde of a finitely supported function f on x, that is functions which are constant on every nz geodesic sphere centered around the reference point O. And sorry, for radial functions this is true, but for a general function, it is the Helgerson Fourier transform f tilde is a function on C cross capital omega, that is the boundary, and is defined by this formula. And since the Poisson kernel satisfies periodicity, so does the Helgerson Fourier transform f tilde. And if our function is radial, then f tilde coincides, that is the Helgerson Fourier transform coincides with the spherical Fourier transform. So now let us define what we mean by the LP Schwartz spaces. So unlike the Euclidean case where we have only one Schwartz space, here we actually have LP Schwartz spaces on X, where P is varying from 1 to 2 closed interval. So the Schwartz spaces, which we shall denote by SPX, is the space of all functions phi on X for which this quantity, that is 1 plus mod of X to the power M and Q to the power mod of X by P times mod of phi X is finite. And the quantity on the left hand side, that is mu pm for every m in non-negative integer, is nothing but seminorm of the Schwartz space, and with respect to this seminorm, SPX is actually a Frechet space. So now that we have defined Schwartz space, we know what is the Fourier transform on the homogeneous trees. We can now define what we mean by multipliers on the LP Schwartz spaces. So we begin by taking a function m, which is an even tau periodic bounded measurable function on R. Then an operator theta, which is defined by the inversion formula for the spherical Fourier transform in this way, is said to be a multiplier on SPX, that is the LP Schwartz space on X, with the symbol mz, which appears here in this formula, if for every seminorm nu pm2 in the range space of SPX, there exists a seminorm nu pm1 in the domain space of SPX and a constant depending on these seminorms m1 and m2, such that this inequality holds. So before we formulate obviously the analogs of Strichartz theorem for a multiplier on Schwartz space with symbol mz, the independent question that occurs to us is, what are the necessary and sufficient conditions one should put on the symbol mz so that theta becomes a multiplier defined by this formula, becomes a multiplier on SPX with symbol mz. To basically give all the necessary and sufficient conditions on M, we need to define another space, which is the H of SP. That is the space of all functions phi from the Helgerson P strip SP to C, which satisfies the following properties. So psi is even and tau periodic on SP, psi is analytic in the interior of SP, and psi and all its derivatives extend continuously on the boundary of SP. So this is the space of all functions H of SP, which satisfies all these three properties. And with this, we have the following characterizations of multipliers on the Schwartz spaces SPX. That is, so consider P greater or equals to 1 and less than 2. Then we have the following equivalence. The operator theta, which we have just defined using the inversion formula for the Helgerson Fourier transform, this thing is a multiplier on SPX with symbol mz if and only our function m is in this space H of SP. That is, m satisfies all these three properties. That is, m is even and tau periodic on SP, m is analytic in the interior of this Helgerson P strip, and M and all its derivative extends continuously on the boundary of SP. So let us now see some key examples of multipliers, some notable examples of multipliers on the Schwarz spaces on homogeneous trees. The first example is an obvious one, that is the Laplacian, and it is a multiplier in SPX with symbol gamma z, because gamma z is an entire function and therefore it satisfies all the properties that are required for it to be in H of SP, and therefore it is a multiplier on SPX with the Laplace for the Laplacian L. In fact, for any polynomial P, if we take P of L, then P of L is also a multiplier on SPX with symbol P composition gamma z, because gamma is entire, P is also an entire function. So therefore P composition gamma is also an entire function. So exponentials for every xi complex constant, the complex time heat operator, that is e to the power xi l, defines a multiplier on SPX with symbol e to the power xi of gamma z. Next, we see that the spherical averaging operator, which we shall denote by S of n, is also a multiplier on SPX, whose symbol is given by phi z of n. Here, n is the sphere on which we are taking the radius of the sphere on which we are taking the spherical average. And lastly, the ball averaging operator, that is B of n, is also a multiplier on SPX. Here, B of n means the ball averaging operator, where the average of function is taken over geodesic balls of radius n. And it is a multiplier on SPX whose symbol psi zn is given by this complicated looking formula, but it can be calculated. So now, before we go again into the details, let's revisit the case of the Laplacian. So in the language of multipliers actually, so that it will give us some hint to how to generalize it, the theorem of Strichartz for the multipliers. So in doing so, we shall mainly recall these two cases, that is when P strictly lies between 1 and 2. So let's see. So let us assume P strictly between 1 and 2, and we know that the Laplacian L is a multiplier for these values of P, is a multiplier on SPX with symbol gamma z, right? Observe that the LP prime infinity point spectrum of L is nothing but the range of the holomorphic map, that is the symbol Z going to gamma Z with domain SP. And Strichartz theorem is basically saying the following. So we are taking a singly infinite sequence of functions on X, satisfying this norm estimate, and L of Fk is equals to Fk plus 1 for all k in the singly infinite sequence, where our non-zero complex constant A satisfies mod of A is equals to gamma of ideal P prime. And what is gamma of ideal P prime? It is nothing but the minimum modulus of gamma Z such that Z lies in SP. That is the minimum modulus of the range of gamma with SP as its domain. We will see. And we observe that the range of gamma, if we take the minimum modulus to be our mod of A, then the range of gamma with the domain as SP intersects this circle at only one point, namely gamma of ideal P prime. And similarly, if we take the negative side of the sequence which satisfies this estimate, where the recurrence relation L of minus Fk is equals to AFK plus 1 is satisfies for some A, such that mod of A is equals to gamma of tau by 2 plus ideal P prime, which is nothing but the maximum modulus of gamma Z. And the range of gamma with SP as its domain intersects this maximum modulus circle at only one point, namely gamma of tau by 2 plus ideal P prime. And from these two hypotheses, we actually conclude that F naught is either an eigenfunction with eigenvalue gamma of ideal P prime or gamma of tau by 2 plus ideal P prime, right? So let us again go back to the picture to verify whether what we have just discussed is true or not. So let's see. So here what we do, so this is the range of gamma under with the domain SP, which is basically the LP prime infinity point spectrum of L, right? And first we take the minimum modulus, and the minimum modulus occurs at this real point, that is gamma of ideal P prime. And here only the characterization is possible. And this range actually intersects this minimum modulus radius circle only at one point, gamma of ideal P prime. Secondly, if we take the maximum modulus with that recurrence relation, that is mod of A to B as gamma of tau by 2 plus ideal P prime, we see that this range, gamma of SP, intersects this circle only at one point, gamma of tau by 2 plus ident p prime, and correspondingly f naught is an eigenfunction with respect to these two eigenvalues. So let us now see what happens if we replace this L by a general multiplier theta with the symbol m, right? So let theta be a multiplier on SPX with symbol mz, and suppose our A in C star, that is this estimate anyway is not going to change because it doesn't involve any multiplier specific condition, but we change this condition to theta of f of minus k as A of f of minus k plus 1, where A is a non-zero complex constant which satisfies maximum of modulus of mod mz, z is in SP. But the difficulty is the range of A may intersect this circle, that is the maximum modulus circle, at more than one point. Example, so this is the example. So if we take the multiplier to be as I minus L, then the symbol becomes 1 minus gamma z. Gamma z is the symbol corresponding to L. So we are basically perturbing the elliptic region, and the range of the symbol m, that is the weak LP prime infinity spectrum of I minus L, becomes m of SP, which is this thing. And what is the maximum modulus? The maximum modulus is basically m of I del P. But when we draw a circle with radius maximum modulus, we see that it actually intersects m of SP at 2 points. Then what should we do? Then is f not an eigenfunction with respect to this eigenvalue or this eigenvalue? We don't know. However, it turns out that f naught can be decomposed uniquely as two other functions, f1 and f2, so that f1 is an eigenfunction corresponding to m I del p prime, and f2 is an eigenfunction corresponding to m of tau by 2 plus I del p prime with respect to this multiplier I minus L, and that is what we have proved in generality. So let us assume P strictly means bigger or equals to 1 and strictly less than 2. As I told that we have not dealt with the case P is equals to 2. And let theta be a multiplier on SPX with symbol mz, satisfying mz not equals to 0. That is, mz is a non-zero, means we take theta to be a non-trivial multiplier. And suppose that f is a bi-infinite sequence which satisfies these two conditions, where the reference relation holds for some a such that mod of a is equals to maximum modulus of mz. And we again assume that the range of A intersects this maximum modulus circle at finitely many distinct points, that is A1 to AJ. Then F naught can be uniquely decomposed in the form F naught 1 plus F naught 2 to F naught J, such that each of these pieces belongs to the LP prime infinity of X, and each of these pieces are actually eigenfunctions of the multiplier theta with eigenvalue, which is the range of intersection of this, the points of intersection between the range of M and the maximum modulus circle that we have here. And similarly, here we take a bi-infinite sequence because we never know whether M0 belongs to the range of M. That is why, just like the P is equals to 1 case that we have seen for the Laplacian. Similarly, the minimum case, so here we take, obviously, we need the minimum to be non-zero because harmonic functions and particularly zero eigenfunctions cannot be characterized. So we take theta to be a multiplier of SPX associated with the symbol mz, satisfying mz not equals to 0 for all z, so that our minimum modulus mod of A is non-zero. And suppose that the range actually intersects this minimum modulus circle at finitely many points, that is A1 to AJ, then F naught can again be uniquely decomposed in this form, with every piece being the eigenfunction of theta with eigenvalue AI, where AI to AJ is nothing but range of A intersecting this minimum modulus. And here we take obviously a one-way infinite sequence as we did for the Laplacian case, because the LP prime infinity point spectrum of the multiplier theta is away from 0, because we already know that the LP prime infinity point spectrum of L is nothing but M of SP, and M of Z is non-zero for all Z in SP. And here also, if our M is, if the LP prime infinity point spectrum of L is away from 0, then we see that only one weight sequence is enough to characterize the eigenvalues for which mod of A is maximum of means the maximum modulus of mz for Z in SP. Then also a similar thing occurs. But in these three theorem, what is important to note here is that in each of these theorem, we decompose actually F naught into sum of eigenfunctions of the multiplier theta, isn't it? In all these three theorems. So is it possible to further decompose these eigenfunctions, that is f naught 1, f naught 2, and f naught j, as eigenfunctions of the Laplacians? So the answer to this question is yes, but we are unable to prove for general multipliers, but we have proved for certain functions of the Laplacian, and not just any functions. Here is the setup. So let us take capital psi to be as a non-constant holomorphic function defined on a connected open set containing gamma of Sp, so that psi composition gamma, since gamma is an entire function, becomes analytic, tau periodic, and everything that is required to be in H of Sp. And hence, gamma composition psi corresponds to a multiplier on Spx, which we shall denote by psi of L. Some eminent examples of such functions of the Laplacian are the polynomials. We will see the spherical and the ball averages also are functions of the Laplacian, and the heat operator is exponential function of the Laplacian, as we have already seen. For these, that is the function of the Laplacian, we actually have proved the following theorem. That is, all these conditions are the same. That is, psi of L is a multiplier on Spx, and we have seen it is associated with the simple psi composition gamma, and if K satisfies this relation with mod of A being the maximum modulus of the symbol, then we can actually decompose F naught as pieces, where each piece is an eigenfunction of the Laplacian corresponding to the eigenvalue alpha gamma of alpha m plus I del t prime. And what is alpha m plus I del t prime? These are actually the points where the maximum modulus is achieved. And we can only have finitely many points like this due to the identity theorem, actually. And similarly, the analog of the second theorem for that is this, the analog of this part for the minimum part, that we have got this result, and this is actually the same thing. And the third one is this. So now we shall apply these three results to get some consequence to some particular cases of the multipliers, such as the spherical averages and the heat operators, and see what are the interesting corollaries or the Strichartz theorem for the spherical averages and the heat operators. So let us denote chi of SON. SON means the geodesic sphere centered at origin and radius n. With the indicate means then chi of SON denotes the indicator function of the sphere SON, and the spherical average of a function over a geodesic sphere is given by this formula. And observe that the spherical average of a function over a zero radius sphere is nothing but the identity function, and one radius sphere is nothing but f minus L of f. That is, we have already discussed the case here. This is basically the spherical average where the radius is taken to be 1. And for n greater or equals to 2, we have such a recurrence relation for the spherical average, that is Sn of f is given by this reference relation. And using this reference relation, one can actually say that the spherical average of a function over n radius sphere is actually a polynomial of L, where Pn is a polynomial of degree n. This n and this n is same. And obviously, the multiplier of this spherical average is nothing but the Fourier, that is the spherical Fourier transform of 1 by modulus of SON, chi of SON, and which is z going to phi z of n. So the maximal modulus of z going to phi z n is on Sp is actually phi I del p prime of n, which also cuts at minus of pi tau by 2 plus I del p prime of n, and is attained at z1 and z2 of this form. And the range actually contains 0, and therefore we need to take a doubly infinite sequence, and our mod of A satisfies the maximum modulus of this, that is phi of I del p prime of n. Then since it is achieved at 2 points, that is the range intersects at 2 points, so f naught can be uniquely decomposed at f naught 1 plus f naught 2, where each of the piece is in LP prime infinity, and one is actually an eigenfunction of L with respect to the eigenvalue I del p prime, and the second one is an eigenfunction with respect to tau eigenvalue gamma of tau by 2 plus I del p prime. So this is the corollary for the spherical averages. Now let us see what happens if we take the heat operator. So for a non-zero complex constant xi, the complex time heat operator is given by this convolution or formula, where xi is nothing but the heat kernel, which is the fundamental solution of the heat equation on homogeneous trees. And obviously, the symbol of this multiplier, that is h xi, is basically the Fourier transform of h small h xi, that is the heat kernel, which is e to the power xi of gamma z. And obviously, being an exponential function, the range, that is with domain as sp, does not contain any zero. Therefore, one can take a one-weight sequence to characterize the eigenvalues using the Strichartz theorem. And for p between greater or equals to 2, 1 and less than 2, we define this quantity, and this quantity is defined just to see the maximum modulus and the minimum modulus of this symbol is basically exponential of real xi plus 5 p xi, and the minimum modulus is real xi minus 5 p xi. And let beta 1 plus ideal p prime, that is z1, and beta 2 plus ideal p prime, that is z2, be the set of points for which this thing is satisfied. And these are the points at which the maximum and minimum modulus are achieved. And therefore, with this, we have the following theorem. That is, if we have a xi means non-zero complex constant, then for p between greater or equals to 1 and less than 2, we consider a doubly infinite, means bi-infinite sequence on x, such that LP prime of infinity x norm of fk is less or equals to m, and then we take a one-weight infinite sequence to characterize the maximum modulus, and the positive way sequence to characterize the minimum modulus as follows. And this is all we have. So thank you. And these are some references that here actually this is the original paper of Rowe, and this is where the story actually began, and its n-dimensional generalization was proved by Strichartz in this paper. And then we actually proved the theorem of Rowe and Strichartz on homogeneous tree in this paper, and later generalized it to the multipliers in the collaboration with RPS in this paper, that is a theorem of Strichartz for multipliers on homogeneous trees. Regarding its extension on abstract spaces, we have this paper which deals with the variants of the Strichartz theorem for the Laplace-Beltrami operators on rank 1 symmetric spaces, whose generalization to multipliers was actually taken up by Nayak and Sarkar in this paper. And these two papers are basically, this paper deals with the two-step nilpotent version for the sub-Laplacian, and this paper deals with the some particular cases of multipliers on Euclidean spaces. So that's all. Thank you.
Hello. Thank you, Sumit, for a nice talk. And
Thank you.
okay, so are there some questions from the audience?
Hello, this is Pradeep.
Yes, Pradeep.
Yeah, okay, you should share the screen because people will ask from that. Yeah. Ask Pradeep.
So So why p less than or equal to only consider what about p bigger than 2? What was the reason for not considering
for
p?
For p bigger than 2 actually means everything depends on the point spectrum, right? For p bigger than 2, the AP prime infinity point spectrum of L, and more generally for any multiplier operator is absent, means that is only the zero function.
Zero is only.
So that is.
And suppose we have a capital A, which is going to be eigenvalue, right? In the theorem, Strichartz theorem you are considering. If modulus of A, there are eigenvalues like so infinitely many eigenvalues whose modulus is same as modulus of A. In that case, nothing can be said. Like
no, actually, in that case, theoretically, it is possible that the maximum
way you
modulus is
constructed the example
infinitely many. Yeah.
My claim
Here
is that the way you constructed the example. Sorry, continue. Tell me.
Oh, so means actually we took our motivations from the spherical averages. And here actually there are finitely many points where the maximum modulus is achieved. So that is why, but if we consider see the nature of the multiplier m corresponding to, nature of the symbol m corresponding to a multiplier theta, we see that m can actually intersect the maximum modulus at infinitely many points as well, theoretically. But we don't know, then how can we actually decompose f naught in what forms? Or countably infinite, maybe it occurs as a sum, maybe, I don't know.
As the integration over the parameterization, something.
Or maybe if there are uncountably many points, then there can be integration and all those things, but we still don't know what happens.
Okay. Yeah. Thank you.
Jerry, the thing is for multipliers, which for symmetric spaces, which I have done, or with this RPS. The thing is, we have really given a different proof for this ball multiplier and another thing for hit kernel thing. So so your proof is unified or no?
We can get it as a corollary.
Okay.
We can get it as a corollary from the general setup actually.
Then it is an IISER.
Apart from what we have for the Laplacian, Laplacian also falls under this category. We have done it for a general, on a broader context.
Okay. Are there any questions from the audiences? So if not,
what is the proposition on characterization of SP multipliers?
Yeah.
So these two are both sidewise, right? I understand that if theta is a multiplier on SPX, then M should satisfy all these conditions. But how do you prove the other way around? Can you share some idea? Like if M satisfies all these conditions?
To take, we have to just use the convolution structure actually, because one can actually lift the function to convolutions by using the S2 space, because on S2 we have a isomorphism. We know that on SP we don't have any isomorphism, that is LP star spaces, but on S2 it actually holds, and therefore we can lift it to convolutions, and then on convolutions we can play this game. So
yeah, so first you go to S2 using that result of the Cowling or
isomorphism.
The Cowling result.
Yes.
Okay.
Yeah.
And from there you go to SP.
So once we get the convolution structure, and then we can actually use the density argument and all those things to extend it to bounded operators on the Schwarz spaces.
Okay, thanks.
Okay, are there any further questions from the audiences? If not, let us thank the speaker for a wonderful talk. Okay.
Thank you, Munadar.